Okay, so let's continue from where we left last time. So we have seen so far that we can remove the divergences in Green's functions by renormalization. Okay, and there are various renormalization schemes, and I have mentioned three of them: MS bar, and also on-shell renormalization. Okay, you can also have off-shell renormalization. So, and we have also seen that our results will depend on mu. Okay, the Green's functions that we write. So let's try to understand what things change and what things do not change when you do a renormalization. Okay, so that's what I want to talk about in this lecture. So let's first try to understand what we mean by a given theory. Okay. So let's suppose that an action is given to you, which is phi 4 action. Okay. This is the bare action or bare Lagrangian here in the square brackets. Or even more appropriately, bare Lagrangian density, okay, in 4 dimensions. So let's go to d dimensions, where d is 4 minus 2 epsilon. Okay, let me not write it. I will introduce that when I write the renormalized field. Okay, here lambda is dimensionful. Okay, as you know, it has dimensions mu to the 2 epsilon. Okay, or if you wish, you can introduce some mu naught and put lambda times mu naught power 2 epsilon. Okay, so let's keep epsilon fixed. Okay, I want to keep epsilon fixed because then things are finite. Okay, they become singular when epsilon goes to 0, but things are finite as epsilon is fixed to some non-zero value. Okay, so given this action and given these bare parameters, okay, now they are not singular. Okay, they are singular only when epsilon goes to 0. So I fix epsilon, and the reason I am fixing epsilon is so that I don't run into this trouble of infinities. Everything is finite but large because epsilon is not really 0. Epsilon is not. Epsilon is somewhat close to 4, close to 0. So things are large but not infinite because epsilon is some fixed number. Okay. So let's see what we mean by saying that this gives us a theory. Okay, this specifies a theory, choosing some values of m square and m and lambda. Okay. So suppose I take this action or take this theory and find out what the physical mass is. Okay. So I figure out what the physical mass is from this theory. What will be the inputs? The inputs will be m and lambda, right? You choose some value of lambda, some value of m, and that will give you some value of mp, physical mass. Okay. Now, if you were to change the values of m and lambda, these bare parameters, if you were to change them, then the value of physical mass would change. Now you have a different theory. Okay, suppose some values of some choice of m and lambda gives you particles in this theory which have mass 1 GeV. Okay, I'm just randomly saying some number. You can take other numbers also. But let's say some choice of m and lambda gives you particles in this theory which have mass equal to 1 GeV, meaning MP is 1 GeV. And if you were to change these values of m and lambda to some other new values, it could be that the new mass becomes now, let's say 15 GeV. Now this is a different theory, right? Because in the first theory, the particles had mass 1 GeV, and in the second theory, the mass is 15 GeV. The action looks the same, but the parameters that appear take different values. Okay, so changing these values will give you particles of different masses. So you are in a different theory. Okay, the same thing I could say in another way. Suppose you look at some cross section. So you are doing a scattering in some collider, and you collide, let's say, 2 particles to 5 particles, these scalar particles, and produce 2 final state particles. And you want to find out the cross section for this production, okay, that you can calculate inputting your chosen values of m and lambda. You'll get a certain prediction, and using that cross section you can try to find out that if you were to collide, let's say, a billion such pairs, so billion of this and these particles, okay, input that into your calculation. So use cross section and this number of collisions, okay, and multiplying them will give you the number of events in which you are going to see these final state particles. Okay, whatever you have kinematical configurations you have specified for these particles, okay, according to that you can find out the number of events that you are going to see when you collide, let's say, 1 billion of such pairs. Okay, let's say you get 100. Let's say you are going to see 100 events in which these final states are produced, okay, when you collide 1 billion such pairs of particles in the incoming state. Okay, and that result is for some choice of m and lambda. Now you change the values of these Bayer parameters m and Bayer parameter lambda to some other value, keeping epsilon fixed. Okay, I don't change epsilon, otherwise things become infinite. It becomes difficult to talk. So let's keep epsilon fixed. Let's pretend our world is not 4-dimensional but 4 minus 2 epsilon dimensional. Now changing these values of m and lambda would change the cross section. Okay, cross section has these modem squares, amplitude squares, okay, and which is what contains the dynamics. The remaining parts are just kinematical. Okay, so these numbers will change, and maybe now you get, instead of 100, let's say 500 events, depending on what m and lambda you have chosen. So you get 500 events this time. Okay, so clearly that choice of m and lambda which gave you 100 events is describing a different theory than this one in which you get 500 events. Okay, so changing these values of m and lambda will give you a different theory in which the predictions for physical masses, for the number of events that are produced in a particular particular collisions, they all will change. Okay, even though the form of the action is the same, but the parameters are different, and that results in different physical observables. Okay, different values of the physical observables. Okay, so now what I will do is we'll stick to one theory. Okay, and by sticking to one theory means having a particular value of m and lambda, so that all the outcomes are fixed. Okay, there is no ambiguity in what you are going to get in a particular scattering or what you are going to get for the physical mass. They are all fixed now. Okay, so m and lambda are fixed, keeping epsilon fixed, so that I don't run into the trouble of infinities. Okay, so now I want to see the effect of doing renormalization. Okay, what things change when I do a renormalization and what quantities do not change when I do a renormalization. Okay, and we will also come back to this discussion here in a while. Okay, and you will see why I was talking about this. Okay, so let's first look at the S matrix elements. See, we have seen already that the Green's functions they change. So Green's functions change when you do a renormalization, because each field when it gets renormalized picks up a factor of z phi or square root of z phi. So let me now look at the S matrix elements. What happens to them? And of course, I am going to keep the theory fixed. I am not going to change the bare parameters m and lambda. Okay, they will not change. So S matrix element, they are giving you the probability amplitude of a state with labels k1 to km. Okay, transforming into a state with labels p1 to pn, and you would expect that this quantity would be a fixed. Once it is given what theory you have, these probabilities would get fixed, or these amplitudes will get fixed, right? So that's the expectation. So I expect that S should not change if I keep the bare parameters in the theory fixed. Okay, and even if I change other things like renormalized parameters and renormalized fields, even if I change them, but my bare parameters are fixed, the theory should not change, and these S matrix elements should not change. And let's verify whether that is indeed the case. So you recall how it is given. You can go back in the notes and you'll find that the expression is this. I'm writing it slightly differently compared to what I wrote earlier. It's not different, it's just minor reshuffle of the factors here and there. It was this. Okay, remember we had one factor of 1 over root z for each external leg. Okay, and that's why you have 1 over root z m plus n, and you had these factors. Okay, mp is the physical mass. Times the Green's function, m plus n point Green's function, okay, where g tilde is the Fourier transform. The tilde always denotes the Fourier transform. That's what we had seen. Okay, and you also know that g tilde contains the poles, okay, coming from the propagators, right? And what is left after pulling out those contributions from the external leg corrections is the amputated Green's function. Okay, so clearly the S matrix element is the residue of these Green's functions. Okay, if you take the residue of this, so you know this has a pole, so take the residue of the pole, okay, that will give you the S matrix. Okay, so okay, I should have written it slightly differently. Anyway, I can do it now. So let's write it like this. Minor modification. Okay, I'm just writing the incoming and outgoing parts separately. Okay, I'm just distributing these factors over these products. J equal to 1 to n times okay. Now recall what's the structure of 2-point function. Okay, and that's relevant because the external legs, they have the structure of 2-point function. So let's recall what is a 2-point function, and again I'm writing everything in the Bayer theory. Okay, there is nothing, I'm not using the renormalized Green's function, so this is G tilde calculated with the Bayer fields. So G tilde 2 was, we found that it is Iz over p square minus mp square. Okay, where z I had introduced earlier. This z is not the wave function renormalization constant that you have seen here, that I denote by z phi. Okay, plus regular terms. Let me see if I can find out easily where that expression was. Okay, it's not in this file. Anyway, you can go back and see this expression. Okay, that's the structure we already know, that G tilde 2, that is the 2-point function, has a pole at physical mass. So that is what is this denominator telling you. And the residue is I times z. And then you have other regular terms at p square equal to mp square. Okay. And also, when we use the renormalized fields, okay, then G tilde 2 see here, this is the correlator made out of this thing. Okay, you take the Fourier transform of this. Okay, but the fields are Bayer fields. That's the 2-point function. But in this, for this one, it is constructed out of phi renormalized, and you take the Fourier transform, and that's what gives you G tilde 2. Okay, and because phi is z tilde, this I don't think I'm putting tilde, z phi, okay, to the half. So you see, you get a factor of z phi here. Okay, so that is how the 2-point function with Bayer fields, defined with Bayer fields, is related to the 2-point function defined with the renormalized fields. So R is the subscript I use for indicating that I'm using renormalized fields here. Okay, so that's the relation. Also note that Z is a constant. Okay, this renormalization constant is really a constant. It does not depend on P. Okay, so Z of phi does not depend on P. P or P square. So the pole structure here, see the left hand side is a function of P, the right hand side is a function of P, and this factor is a constant, does not carry any P dependence. And I know that the left hand side has a pole at physical mass, so it has a form of 1 over P square minus mp square. Okay, so it has a pole, and then it implies that on the right hand side also since this is the only factor which has p dependence, this should have a pole at physical mass, right? So that it's the same function. Okay, otherwise it cannot be that the left hand side has a pole at p equal to mc square and right side does not have, because it has to be, because left hand side is same as the right hand side. Okay, so we should have poles on both the sides. So it's clear that G tilde 2 defined with renormalized fields also has a pole at the physical mass. Okay, let's look at the residue now. So for that I'll just write the expression close to the p square equal to mp square. Okay, so the left hand side is 1 over p square minus mp square I times z. Okay, I'm just looking at the pole terms. And what do you have on the right hand side? You have a z phi, this factor, and then I have argued that this has a pole. This has the same pole. So it should have I times some residue, let's call it, what I'm calling it, R. Okay, the residue is R divided by p square minus m physical square. Okay, where R is the residue is the residue which you get here. So this is the 2-point function. Okay, and here the fields are renormalized fields. So as I wrote earlier, this is just the Fourier transform of this. Okay, and renormalized parameters. This is this object. So when you calculate this, you know that that's going to give you a pole at the physical mass, and it will have some residue, and whatever residue that you are going to get, I am denoting by R, or rather I times R. Okay, so from here you can see that Z is Z phi times R. Okay, or the residue that you are going to get in the renormalized theory is Z over Z phi. And of course, if you choose a renormalization scheme such that this R is 1, right, you can choose such a renormalization scheme so that you get, we have already done that before. Let's see here. Here. So with these choices, yeah. So we had demanded that we want to put we want to use a scheme such that the propagator comes out to be I over p square minus mp square. Okay, so that the residue is 1, and then you can find out what conditions you have to impose. Okay, so this is what we have done here. So you could ask for that, and if you ask for such a condition to be satisfied, that R should come out to be 1. Okay, then Z is same as Z phi. Okay, or the wave function renormalization constant Z phi is same as the Z which we had introduced earlier. Okay, but in general, if you are not using such a scheme, you will have a residue R which will be different from 1, and it will be related to Z phi and Z by this relation, or this relation. Okay, so now let's see what happens to the S matrix element, given that we know how the residue changes when you do a renormalization. So we see that S matrix element okay, and this I am writing with in the using the bare quantities. Okay. So my understanding is that S matrix elements are physical observables. Okay, these are physical quantities because you are talking about what is the probability amplitude of a state with these labels K1 to Km appearing as another state. Okay, with labels this P1 to Pm. Okay, and it should not change. And let's see what it gives us. So I have product I equal to 1 to m minus I over 2 pi 3 halves 1 over square root of z. Okay, ki square minus mp square so let's go here. So here okay, let me write it. It will take little while to write, but it will be better to do this way. Let me write it again. I'm just writing the same thing again. Okay. Now what I'll do is I'll put this result that Z is Z phi times R. Okay. So here I'll put Z phi times R. So you'll get a root R here, 1 over root R here, okay, and a 1 over root Z phi. Okay. And remember, I'm still writing the same S matrix element. Okay, this is still in the bare theory. Okay, I'm just replacing this. And G tilde m plus n, this is just like what you have here with two fields. This is an object constructed out of m plus n fields. Okay, and each field, when you turn to renormalized field, will give you a factor of root z. Okay, root z of phi. Okay, so what I'm saying here is that G tilde is the, okay, this has stopped working for some strange reason. It's okay. Fourier transform of, just a second, let me see why it's not working. So it's a Fourier transform of such m plus n fields. Okay, and when I write this as correlation function with phi r, here I will have z phi m plus n. Okay, so root z phi m plus n. Okay, so here if I replace this factor, this will have root z of phi m plus n G tilde m plus n, but the renormalized one. Okay, and you have seen here already that you get 1 over square root of r. Okay, and then you have root z of phi in the denominator. Okay, so root z of phi in the denominator and root r in the denominator, and there are m such factors here and n such factors here. So together they will give you root z phi m plus n in the denominator from here, and you have root z phi to the m plus n in the numerator coming from this part. So the same expression, okay, I can write as the following. One over r, square root of r. Okay, where square root of where r is the residue which you get when you used. Okay, again not writing. When you used renormalized fields and renormalized parameters. Okay, this is getting hopeless. Okay, let me pause. Okay, so n minus I over 2 pi 3 half 1 over square root of r minus mp square times g tilde r. Okay, this is with the renormalized field. So you see, whether you use the renormalized perturbation theory, renormalized fields and parameters, and then calculate g tilde with the renormalized fields, okay, and put the residue that you get in the renormalized theory, that one, okay, or you work with the unrenormalized fields and parameters, you get the same result, okay, which is good, because that is something we should expect, because S is a physical quantity, right? It's telling you these probabilities of transitioning from here to there, and that should be fixed once you fix the theory. Okay, and the theory gets fixed when you fix the bare couplings and bare mass parameters. Okay, so this is good. Let me write this in words. S matrix elements do not change whether we evaluate okay, lots of difficulties today. Whether we evaluate them using bare quantities or renormalized quantities. By quantities I mean fields and parameters. Okay. So that's about S matrix elements. Let us look at Green's functions. Okay, so let's hope this works now. Yeah, I was looking at Green's functions. So let me write down a bare Green's function, which I will write as Gn okay, where these phi's are bare fields. Okay. Now this object is independent of the renormalization scale mu, right? Because bare quantities do not depend on mu. There is no mu in the action. Okay, this mu comes when you write the fields and the couplings in terms of renormalized fields and renormalized parameters. Okay, so when you have lambda r, then only you will get mu. But here, because this is in terms of bare quantities, there is no mu. So it doesn't depend on mu, and of course it doesn't depend on any scheme also, independent of the renormalization schemes. We have not subtracted any infinities. Okay, so there is no reason why scheme should affect this. Now let's write this Green's function in terms of renormalized Green's function. Okay, so Gn is equal to this object which you have here. Now each field phi I will write as z phi times phi r, and remember these are constants. Okay, they do not contain any momentum dependence or any x dependence. So this is root z phi to the n, okay, times Gn, but now with renormalized fields, because we are denoting by Gr the Green's function that you construct with Gr with renormalized fields. And of course this is a function of epsilon, mu and lambda r. Okay, let me write this z also explicitly with its arguments. So z of phi, it depends on epsilon, mu and lambda r. Okay, see, since the left hand side is independent of all this mu and scheme and all these things, but G depends on it, so that the dependence in G has to be cancelled by the dependence in Z. So Z also has to depend on all these variables, epsilon, mu and lambda r and mr also. I should have written mr also. These are the parameters in the theory. But now you see that the original action, okay, or the Lagrangian, had only m and lambda. These were the only parameters in the bare action or bare Lagrangian. Okay. But when you do renormalization, when you write everything in terms of renormalized fields, you are writing in terms of mr, lambda r and mu. Right? So you see that you have two parameters here. So your theory is really controlled by these two parameters. So once you specify what m and lambda is, I'm still thinking of epsilon as being finite. So once you specify for a given epsilon what m and lambda are, then you have fixed everything in the theory, meaning what is the physical mass of particles, that's fixed, what is the probability of producing a certain event, that is fixed. Okay, those things are fixed. But here you see you have, for the same action, for the same theory, instead of 2, 3 parameters. So clearly all the 3 are not independent. Okay, because here you have 2, here you have 3. So it's possible to choose different values of mu. Okay, or let me put it this way. Let's look at the theory from this point of view, where you are using only m and lambda, the bare parameters. Okay, so you have concluded all your conclusions. You have found out what is the physical mass when you have chosen a particular value of m and particular value of lambda. Okay, so given that fixed choice of m and lambda, bare parameters, okay, you have found out what the physical mass is. What is the probability of producing a particular final state let's say, 2-body final state when you are colliding two particles, a 3-body final state when you are colliding whatever number of particles. Okay, you are fixing the initial state, you are fixing the final state, you get numbers. Okay, depending on the initial and final momenta, you have all these big tables of numbers. Okay, now you choose some value of mu. Given that value of mu that you have chosen, find out lambda r and mr, these numbers, what their value should be, such that you reproduce those entries in the table. Okay, meaning you reproduce exactly the same physical observables having the same physical values given the choice of mu you have made, okay, and the lambda r and mr. Okay, so once you do that, you are still talking about the same theory. Okay, because all physical observables are same whether you choose m lambda or mr, lambda r and mu. Now what you do is, because you have 3 parameters here, okay, you choose a different value of mu now. Okay, now choosing a different value of mu will still be okay, because you will be able to change lambda r and mr. Okay, because not all 3 are independent, so accordingly you change values of lambda r and mr such that all the physical observables are reproduced exactly the way they were before. Okay, meaning your new choice of mu and accordingly adjusted value of lambda r and mr, they should give you exactly the same physical mass as you had earlier, and the same values for other observables. Okay, so that you can claim that you are still talking about the same theory and not different theory. Okay, and this will happen simply because you have 2 parameters here and you have more than 2 parameters here. So there is a redundancy in choosing in these parameters. Okay, so you have 2 here, 3, so you can choose one of them and vary it, and accordingly you should vary these lambda r and mr such that m and lambda do not change. Okay, the effect is what you want to arrange is that changing mu should not change m and lambda, and that you achieve by correspondingly adjusting the values of lambda r and mr. Okay, which means that once a theory is given to you, and by a theory I mean these values of these observables are fixed, then these parameters m and lambda are really dependent on the choice of mu you make. Okay, so instead of writing just mr and lambda r, I should write mr of mu, lambda r of mu. Okay, these things. So for a given theory, meaning given choices of lambda and m, we can change value of mu provided we adjust or we change the values of mr and lambda r such that lambda and m do not change, right? Because lambda is a function of lambda r, mr and mu, and m is a function of lambda r, mr and mu. Okay, and if I could arrange that lambda and m do not change even when I change mu, then clearly all the predictions for the observables, they will not change. Okay, so I should write then Gn x1 x2 up to xn is equal to z phi n over 2, where z depends on these variables. Okay, now I am making this notation explicit by putting mu as an argument of lambda r. And of course, it also depends on the external momenta. Okay, that's also a parameter. So you see that z till z phi depends on mu both explicitly and implicitly. Both explicitly and implicitly through lambda r and mu r and mr, sorry. Okay, so there is a mu dependence that comes through the arguments of mr and lambda r, that is the implicit dependence, and then you also have an explicit dependence on mu here. Okay, let me go back and show you somewhere here. Okay, I don't think we have it here, but you see what finite parts you subtract is up to you, and any dependence on mu that you get, okay, when you are renormalizing, that also you can subtract, okay, because mu is some finite, you have chosen it to be some number, that also you can subtract, some mu dependence you can subtract. So this renormalization constant z will in general depend explicitly also on mu, because you are subtracting some finite parts. Okay, now here is a remark that when you are doing MS scheme or MS bar scheme, okay, in these schemes, in these renormalization schemes, you only subtract the pole parts, and also in the MS scheme and in MS bar you also subtract things like log 4 pi and Euler gamma. Okay, so at one loop, of course, this is how it appears, and it's clear that at one loop z phi will not depend explicitly on mu. Okay, because what you are subtracting will only have the pole and no mu dependence. Let me go back and show you. I hope I'll find it this time. Here. Okay, so this z lambda zm, they depend only on lambda r here. Okay, there is no explicit mu dependence. So here, now I have already argued that lambda r should really be written as lambda r of mu. So the mu dependence in z comes through the dependence on lambda r. Okay, that's a statement, of course, true at one loop, because that is something you have seen explicitly. But it is true that this statement is even true to all orders. Okay, no matter at what order in lambda r you are, the dependence on mu will be only through lambda. Okay, and also mr will not depend on, will not appear in z phi. So this is an all order statement. I am not giving you the argument for it, but I am just stating the result. So the remark is the following: in MS and MS bar schemes, okay, where we subtract only the pole terms, the dependence on mu in the renormalization constants Zi, where I is phi or m, enters only through the coupling constant. and it doesn't depend on mu explicitly. And it also does not depend on MR. It cannot depend on MR because you see Z is 1 plus something. Now 1 is dimensionless, and if mu is not allowed, it cannot appear explicitly, then MR cannot also appear, because if MR appeared, then the object will be dimensionful. Okay, the term that you will be writing will be dimensionful. The only way MR could appear would have been if mu also appeared, because then you can make such ratios, MR over mu, which is dimensionless. So it would make sense to add such a dimensionless function to a dimensionless quantity here. Okay, but since mu cannot appear, okay, MR can also not appear. So it's not so evident from one loop calculation that mu will not appear, but it's something you can argue that whatever mu dependence might appear gets cancelled, okay, when you are looking at MS or MS bar scheme. So in such schemes, which is MS and MS bar, our renormalization constants we should write as, so in general these are dependent on all these objects, but in these schemes they only depend on epsilon and lambda r. Okay, so this is good, something we know about the dependence of these renormalization constants on mu, and that is something we are interested in, because if you look at the Baire-Green's functions, this does not depend on mu, right hand side does, and Gn depends on mu in a certain way. Okay, square root of z depends on mu in certain way, such that the dependent gets cancelled, because on the left hand side you have mu independence. Okay, so we will analyze further these objects in the next video.